All right, welcome to this explainer. Today, we're taking on what a lot of folks consider the absolute boss level of object-oriented programming, polymorphism. If you've ever felt a little, overwhelmed by OOP concepts, don't worry, you're in the exact right place. We're going to treat this like your ultimate exam prep session. Our core mantra today is super simple. One interface, many different forms. By the end of this, you're going to know exactly how to nail those tricky exam questions and, honestly, write incredibly flexible code. So, let's get into it. Here's the game plan for today. We'll start by defining what polymorphism actually is. Then we'll dive into overriding, which is dynamic polymorphism, followed by overloading, or static polymorphism. After that, we're going to look at the famous duck typing trick, and finally, we'll wrap up by seeing how this creates super flexible code in practice. Okay, part 1. What exactly is polymorphism? To really wrap our heads around this, it helps to look at the Greek roots of the word. Poly literally means many, and morph means forms. You mash those together and you get many forms. In the programming world, this is just the magical ability of different objects to respond to the exact same method call, but they do it in their own totally unique way. It's brilliant. So, picture this. You're sitting in your computer science final and your professor throws this classic question at you. If different objects share a method name but act completely differently when that method is called, which OOP principle are we talking about? Take a second, lock in your answer in your head. It's polymorphism, for sure. The big takeaway here is that you absolutely do not need to write 20 different function names for 20 different types of objects. The system is actually smart enough to know what to do based on the specific class of the object you're interacting with. This cuts down on so much repetitive code. Moving right along to section 2, overriding, which is our dynamic polymorphism. Let's look at a really common exam scenario. Say you've got a parent class called animal, and it has a method called sound. Then you create a child class called dog that inherits from animal. The question is, what's the exact output when that dog object explicitly calls the sound method? Think about the comparison here. The base animal class defines that sound as something like general animal sound. But our dog class has its own specialized sound method that outputs bark. When the dog object speaks, it totally ignores that generic sound. It completely replaces or overrides the parent's behavior. Under the hood, it's actually really straightforward. When your code runs, the interpreter checks the dog class first. It says, hey, does this specific dog have its own sound method? If it does, boom, it executes it immediately. That's overriding. We call it dynamic because the computer is making this call while the program is actively running. Now, if the dog class didn't happen to have that method, only then would it fall back and ask the parent animal class. All right, part 3, overloading or static polymorphism. Now, here's a bit of a trick question that professors love to use to test your knowledge across different languages. How do we achieve compile time or static polymorphism? And does Python support it natively? This is where things get interesting. Overloading happens at compile time. So in languages like Java or C++, you can totally have multiple methods with the exact same name, as long as they take a different number of parameters. The compiler sorts it all out before the code even runs. But Python? Python doesn't actually support traditional overloading natively. It leans heavily on dynamic runtime overriding. However, Python developers have some really clever workarounds using default parameters and special methods. A perfect example of this workaround is overloading Python's built-in dunder methods, those ones with the double underscores. Normally, if you just print a standard Python object, you get this super messy, unreadable memory address. But if you overload that underscore str method inside your class, you can instantly transform that ugly output into clean text like car brand, Toyota, model Corolla. You're literally customizing how a built-in function interacts with your specific object. It's so cool. Okay, section 4. This is a really fun one. The duck typing trick. Let's test your understanding of inheritance with a quick true or false. Does polymorphism strictly require classes to inherit from a shared parent class? Like, does a dog have to inherit from animal for this whole thing to work? To answer that, we lean on a famous old programming proverb: if it walks like a duck and quacks like a duck, it must be a duck. This is the absolute core of Python's philosophy. Python really doesn't care about a strict family tree. It cares about behavior. It only cares about what an object can do, not what it inherently is.
So the answer to that question is false. Inheritance is not strictly required for polymorphism in Python. It's all about the methods. This gives you insane flexibility. Think about it. You could have a car object and a person object, obviously entirely unrelated things biologically and mechanically, but if they both have a method called move, for example, you can toss them into the exact same list and trigger that move method in a simple loop, and your program won't crash. One interface, many forms, right?
Finally, Section 5, Flexible Code in Practice. For this last test, let's step out of the classroom and into a real-world scenario. Why would you want to use polymorphism when you're building, say, a real-world payment system? Imagine you're managing credit cards, digital wallets, and bank transfers all in one application. How does polymorphism actually save you here? The difference in the architecture is night and day. On one hand, you have rigid, amateur code. It relies on endless if-else statements, checking the exact type of payment before it calls the pay function. If you need to add a new payment type tomorrow, you've got to rip open and rewrite that code. But on the other hand, you have elegant, polymorphic code. It's literally just one line, paymentMethod.pay. Because every single payment class has its own specialized pay method, the system automatically triggers the correct process. No messy logic required. Just to recap the absolutely huge benefits here. Polymorphism drastically cuts down on repetitive code. It makes maintaining your application practically effortless, and scaling so easy. If you want to add a crypto payment option, you just create a new class with a pay method, and the rest of your system stays exactly the same. It perfectly follows the open-closed principle. Your code is open for extension, but completely closed for modification. And there you have it. You are fully equipped to absolutely crush any question on object-oriented polymorphism. But, theory is kind of useless without practice, so I want to leave you with this. Now that you've mastered the power of one interface, many forms, how are you going to use it to transform your next coding project? Seriously, drop your ideas down in the comments. Thanks so much for hanging out with me on this explainer, and hey, happy coding!